Okay, so let's move on to the next chapter. Chapter 7 in the climate modeling book by Tom Stoker is on large-scale circulation in the atmosphere. Just like ocean, here we tend to focus on the dominant features in the large-scale circulation. In the ocean, we looked at western boundary intensification, wind-driven gyres, and so on. Here we will look, of course, at the Hadley cell and some mid-latitude features where there are hydrodynamic instabilities, what are called baroclinic instabilities. Remember, we introduced the concept of barotropic and baroclinic structures in the vertical tend to be baroclinic if there is a if the isobars and isotherms or dense density surfaces are not parallel to each other, and it's barotropic if they are parallel to each other. So remind ourselves again the governing equations for the large scale motion. We had the full terms du dt, u du dx, v dv dy, w du dz, and we had the pressure gradient, wind stress forcing, and Coriolis. We had similar expression in the meridional direction. In the vertical, we obviously ended up doing the hydrostatic assumption by assuming that dw dt, capital D, the total derivative is 0. So the vertical scales are much smaller than the horizontal scales. The other important thing in the atmosphere compared to the ocean is that atmosphere is highly compressible. So we cannot use the equation we used in the ocean for continuity equation. So here we have to carry density. So d rho dt equals minus grad dot u rho is the continuity equation with no mass source or sink, obviously. Density is an inconvenient variable, but the atmosphere can be treated as an ideal gas even when it has water vapor in it. So rho equal PRT, P equal to rho RT, sorry, is the ideal gas law, and so we can replace density with pressure and temperature, which are much more easy to measure and track and so on. The most important thing again in the atmosphere is how fast the atmosphere moves with respect, like compared to the ocean, where ocean waters are heavier, 1,000 times heavier than air, and ocean currents move at typically centimeters per second, whereas atmosphere tends to move in tens of meters per second in terms of winds, sometimes even at the surface, right? So the momentum conservation then requires that Earth, which has a large circumference at the equator, air parcel will be moving at almost 1600 kilometers per hour to rotate once in 24 hours with the Earth. But as you go to higher latitudes, the circumference is much smaller. So if you take an air parcel that's on the equator at, let's say, at rest and moving with the Earth, and you move it north, then it is carrying the eastward velocity at the equator, which is much larger than the eastward velocity at higher latitudes, which means it'll begin to accelerate in the eastward direction, or we get westerlies. So that's what this equation is saying. Angular momentum, specific angular momentum, because we have dropped the mass here, so this is per unit mass, is omega r cosine phi, which is the local radius at any latitude phi, plus u is the relative zonal velocity of the parcel with respect to Earth, so it's what we measure when we are on Earth, times r cosine phi, so that gives us omega r, so that's the angular momentum at distance r cosine phi from the axis of rotation. We can use this by setting the u to be 0 at the equator, because the air parcel is moving with the Earth and doesn't have a relative velocity u, and cosine phi is 1, so we get omega then we can solve for u phi at any latitude as simply omega r sine squared phi divided by cosine phi. That's what will be the zonal velocity at any latitude phi. Okay, you can yeah, so you can do that very easily by writing out the equation. I hope I have it right. Omega sine phi cosine phi. Yes. Yes. I have it derived in another equation on dynamics where you can look at the podcast. So what does this say? Basically it says that as phi increases, remember that cosine phi is 1 but cosine pi over 2 is 0. So as phi increases, cosine phi decreases, so u begins to increase, and by the time you reach about 30 north, this angular momentum conservation, which is valid in the upper atmosphere where there are no frictional forces and so on, then it very quickly reaches unrealistic values of, let's say, 130 some meters per second, which is obviously about 3 times larger than what is actually observed, which means the angular momentum is not being conserved. Somehow the momentum is being pulled out as the air parcel moves to higher latitudes. So you can go back to observations and look at the stream flows in meter per second, geopotential height in meter at 200 millibar, which is in the upper atmosphere. So we're looking at mean wind field at an altitude of around 12 kilometers. Data is from ERA40, which is a European Union reanalysis product. We haven't defined geopotential height. It's basically related. So pressure decreases logarithmically, exponentially as we go from the surface to the upper atmosphere, and we can find the relation between the physical height, altitude z, and pressure p using this relation between height and pressure. And it's convenient to express the atmosphere in the vertical with these geopotential heights, especially assuming that the gravitational acceleration g does not vary with height. I will show the equations in a minute. So geopotential height tends to give us indicators of the distribution of temperature in the vertical, in the atmosphere. So basically we want to see that there are these very strong upper level winds at 200 millibar which are in the jet stream. So there are typically two jet streams, the subtropical jet stream and the polar jet stream, and it is consistent with the idea that angular momentum is being advected from low latitudes where the atmosphere is receiving momentum from the Earth and it is transporting it northward, and then it is putting it down towards the Earth. Because if the winds are going westward with respect to Earth, we are on the accelerating framework, so this is with respect to Earth, and Earth itself is moving from west to east, means that winds are actually going faster than the Earth itself, and that can only happen if you are bringing momentum from somewhere. So obviously we are bringing momentum from the low latitudes where the angular momentum is high because the circumference is high, to the high latitudes where the circumference is low, and that's also gives us, if we look at the zonal mean meridional section, so if you average across all longitudes and look at a north-south figure, you will see that the winds are fairly weak in the low latitudes where we have the trade winds converging into the ITCZ. When the winds converge, obviously wind speed goes to zero in the middle, but as you go off the equator, you see that winds are increasing from the surface towards the upper atmosphere, and this is the should be annual mean. So these are let's see, annual mean December, January, February, and June, July, August, and obviously there is a seasonality, so you can see that the winter hemisphere has a stronger jet here. This is weaker than here, and this is stronger than here. So boreal summer winter, this jet stream is stronger. Boreal summer boreal summer, boreal winter, boreal summer. This one is stronger because it's the austral winter. Okay, and you can see the vertical profiles here. So you can see that at these latitudes, even the winds at the surface are westerly, which means despite the friction near the surface, winds are going faster than the atmosphere because momentum is being brought down into the lower atmosphere. The other thing we can also look at that is related is the temperature distribution, again in the zonal mean meridional sense. You have warm temperatures in low latitudes, cold temperatures at high latitudes, and of course temperature drop off to the stratosphere, tropopause, and then they increase in the stratosphere because of ozone formation and UV absorption by the ozone and so on. So what you see here is that the warmer temperatures are warmer and warmer at each level, so the gradient from the equator to pole is stronger and stronger as you go in the upper atmosphere. So you can see that here. If you're in low latitudes, the gradient of temperature is smaller, but as you go in the upper atmosphere, the temperatures here are warmer than they are much warmer than here. So the gradient increases, and in the above that the gradient is even stronger. So the pressure gradients increase with altitude, which means the simply remembering the Coriolis relation. If pressure gradient is in this direction and Coriolis can balance the pressure gradient, then the geostrophic winds will be coming at us. So in the northern hemisphere they are being tilted to the right of the direction of motion. So you have the arrowhead coming towards us, which means that wind speeds are increasing with height, which is consistent with this. So you can also think of the horizontal temperature gradients introducing vertical shear here. Okay. The other thing we will need is this, which is showing rainfall distribution. We have the ITCZ. Indian Ocean is complicated because of the monsoon, but you also have the SPCZ and the South Pacific Convergence Zone and the South Atlantic Convergence Zone. But you also have the storm track here, where you have secondary maxima in rainfall as you go from the low latitudes to high latitudes. So there is lots of diabatic heat being released by condensation when rain happens here and also here. So soon we will look at the balance of terms in the atmosphere, large scale circulation, where we have to see where the heating terms are strong and how that affects the meridional circulation that we are looking at here. Okay, so setting that up, I will leave it here and come to the next podcast to explain a few more concepts of how we can explain the large scale circulation with these basic background, basic background material.